Bioinformatics Micromodules, Performing Text Search using Burul's Relay Transform. In this module, we introduce one additional property of BWT and describe how it can be used to perform text search. In the last module, we have already introduced 4 properties of the sorted rotation matrix and BWT. Now, let's talk about a 5th property, which is that if a character appears multiple times in the indexed sequence, the different occurrences of it in the first column and the last column of the sorted rotation matrix have the same order. To see what it means, let's again use our $$ example to illustrate. This sequence contains 4 T's at positions 1, 3, 7, and 8 respectively. To make them easily distinguishable, we color them in green, red, blue, and orange respectively. Now, if we look at the last column of the sorted rotation matrix, we see that T is in rows 2, 3, 4, and 9. The T in row 2 actually corresponds to the red T because it is the T 3 characters after the $ symbol, and thus it is the T at position 3 of S which we colored red. Similarly, if we check carefully, the T in the last column of the 3rd row is the orange T. The one in the 4th row is the green T, and the one in the 9th row is the blue T. Now, interestingly, if we look at the 4 T's in the first column of the sorted rotation matrix, from top to bottom, they are also the red, orange, green, and blue T respectively, which means their order is exactly the same as in the last column. To see why this is the case, notice that when we determine the order of the 4 sorted rotations that end with a T, since they all have this same character at the last position, their order is only determined by the first 10 characters. Imagine now we move these T's to the beginning of the rotations. The resulting sequences are exactly the 4 rotations that start with a T. Since we did not touch the remaining 10 characters of these rotations, they remain ordered lexicographically. For instance, since the rotation ending with the red T ordered first among the 4 rotations that end with a T, the rotation starting with the red T must also be ordered first among the 4 rotations that start with a T, and that explains the property. We now talk about 2 applications of this property. The first application is getting back the original sequence S from the BWT of it B. In the last module, we have already studied how this can be done by reconstructing the whole sorted rotation matrix step by step from B. But this time, we want to do it much more efficiently. To do that, we first view the given B as the last column of the sorted rotation matrix and reconstruct the first column of the matrix, which simply depends on the frequency of each character. For example, since there is $, 4 A's, 1 C, 1 G, and 4 T's, we know the first column of the sorted rotation matrix contains a $, followed by 4 A's, and then 1 C, 1 G, and finally 4 T's. But unlike last time, we only need these 2 columns this time rather than all the columns in the whole sorted rotation matrix. What we do now is a backtracing starting from the $ symbol. We know that in the first column, $ must appear in the first row. What is the character that appears right before $sign in S? By looking at the last column of this row, we see that it is a G. Similarly, now we ask, what is the character before G in sequence S? First, we find that in the first column, G is in row 7. And in that row, the last column contains an A, and so we conclude that in S, the character right before the G is an A. In addition, we know that it is not just any A, but the orange A, and therefore we next ask what character precedes this orange A in sequence S. Since in the first column of the sorted rotation matrix, the orange A is in the third row, we look at the last column of that row and find the orange T there, which means the character right before the orange A in S is the orange T. By repeating this backtracing process, we can finally obtain the whole sequence S back from B without reconstructing the whole sorted rotation matrix. The second application of the property we want to talk about is text search. The way to do it is similar to what we have just done for reconstructing S from B, namely doing a backtracing by searching for the query backward from the last character to the first character. However, this time, instead of tracing exactly one row, we will progressively narrow down the range of rows that contain the query at the beginning of the sorted rotation matrix. For example, if we want to search for TA, if it is contained in the indexed sequence, it must appear at the beginning of some rotations that occupy consecutive rows. What we want to achieve is to find out this range efficiently without reconstructing the whole sorted rotation matrix. The conceptual steps of our algorithm are as follows. First, starting from B, we get back the first column of the sorted rotation matrix, as we have seen before. Second, we determine the rows that have an A in the first column, and we find them from the second row to the fifth row. Notice that this must be a range of consecutive rows because all occurrences of the same character are next to each other in the first column. Next, we check the last column of these rows to see if any of them contain the previous character in our query, which is a T. We find that in the last column, these rows contain the first three T's, or using our colors, the red, orange, and green T's. Since these T's are the consecutive ones in the last column, they must occupy consecutive rows in the first column as well. And we find that they occupy rows 8 to 10 in the first column. By now, we can conclude that there are 3 occurrences of TA in the indexed sequence. If we want to find out where these 3 occurrences are in the sequence, we can make use of the suffix array. We just go to rows 8 to 10 of the array and read the recorded positions there. And we get positions 3, 8, and 1 as the answer. Let's see another example with a longer query. This time, we want to search for CAT. First, we look for T in the first column of the sorted rotation matrix, and we find that there are 4 occurrences of it in rows 8 to 11. Next, we check whether these rows contain an A in the last column, and we find that they contain the third and the fourth occurrences of A, shown in red and orange, respectively. These 2 A's occupy rows 4 and 5 in the first column, and so next, we check whether these rows contain a C in the last column. We find that these rows contain the first occurrence of C. This C occupies row 6 in the first column. Finally, we check row 6 of the suffix array to find out that CAT appears at position 5 of S. As usual, we have only finished a conceptual description of the searching process. But if we actually try to implement this algorithm, there are several problems. First, from the first column, how can we efficiently find out the rows occupied by some particular occurrences of a character, such as the third and fourth occurrences of A? Second, given a range of consecutive rows, how can we efficiently find out which occurrences of a character appear in the last column? For example, in rows 8 to 11, how do we know which occurrences of A are there in the last column? Finally, how can we reduce the space required? For instance, wasn't it because the suffix array requires all the n of n space which we didn't like, that we started introducing BWT? Have we actually achieved nothing because at the end, we still need to use the suffix array to find out the occurrence positions of the query in the index sequence? Let's tackle the first two problems. To find out the rows occupied by specific occurrences of a character in the first column, we actually only need to record the first row occupied by each character. This can be easily done by recording the total number of times each character appears in the sequence. In our example, the first occurrence of $ is in row 1, the first occurrence of A is in row 2, C in row 6, G in row 7, and T in row 8. Now, if we want to find out the row that the third occurrence of A occupies, we only need to find out the third row starting from 2, which means 2 plus 3 minus 1. That is row 4. For the second problem, in order to find out the exact occurrences of a character in the last column of a given range of rows, one way is to store the number of times that each character has been encountered up to each row. For example, for character A, since in the first row we have a G in the last column, which is not an A, we have encountered A 0 times up to that row. Similarly, since the second, third, fourth, and fifth rows are all not A in the last column, we have encountered A 0 times up to the fifth row. The first occurrence of A is in the sixth row, and therefore up to this row, we have encountered A 1 time, and so on. Using these numbers, we can easily determine the occurrences of A within a range of rows. For example, if we want to know which occurrences of A's are there in rows 8 to 11, we first notice that before entering this range, in row 7, we have encountered 2 A's. Then at the end of this range, in row 11, we have encountered 4 A's. Combining these two facts, we know that rows 8 to 11 must contain the third and the fourth occurrences of A. Let's summarize what we have learned about the use of BWT for text search so far. First, we need the transformed sequence B produced by applying BWT to the input sequence S. As discussed in the last module, it can be obtained using a suffix array in linear time. Next, we need to record the first occurrence of each character in the first column of the sorted rotation matrix, which can be obtained by a simple linear scan of the sequence or by doing a binary search of each character using the suffix array. The third thing that we need is a table recording the number of times each character has been encountered up to a certain row in the last column of the sorted rotation matrix. Finally, we need the suffix array, which brings us back to the third problem we talked about before. One way to avoid storing the suffix array in memory is to store it in the secondary storage, such as the hard disk, and do the lookup in batches. Let's visualize all these components using an illustration. Here, we show different types of data in 4 different blocks. The gray block contains data that we do not need to store and are shown just for our reference. The blue block contains data that we fully store in memory. The orange block contains data that we store in a special way that is less expensive, which we will explain later. Finally, the green block contains data that we keep in the secondary storage. First, the original sequence S is only needed at the beginning when constructing the other data structures. It is not needed during the search process. From S, we create a suffix array, for example, by first constructing a suffix tree and then perform a tree traversal. The suffix array is initially stored in memory such that together with S, the BWT of S can be produced. As mentioned, when doing text search, we can keep the suffix array in the secondary storage instead. Next, we create this occurrence count table that we call O, which records the number of times that each character has been encountered up to a certain position of B. Conceptually, we also want to reconstruct the first column of the sorted rotation matrix, but as explained before, we only need to store the position of the first occurrence of each character in this column. We call this table F. One small remark we need to make here is that if some characters are missing from the indexed sequence, there is no occurrence of it, and so the definition of table F that we have been using would be invalid. A more precise definition that is always valid, although not so easy to understand, is that each table entry corresponds to 1 plus the total number of occurrences of the lexicographically smaller characters. For example, since the total number of $signs, A's, and C's in our example is 6, the entry for G in this table F is 6 plus 1, which is 7. A second remark is that the table F and a special form of table O together are called the FM index, which stands for full text index in minute space. So what is that special form of table O? One possibility is to store only a sample of the positions. For example, we may store only the numbers at the odd numbered positions, which can reduce the storage needed by half, although the space complexity remains order n not n. If we do that, when we need to know the value of an even numbered position, we first retrieve the number of the previous position, which is an odd number, and then scan sequence B linearly, which takes constant time to get the actual number we want. The fewer numbers of table O we store in memory, the more time we need in these linear scans of sequence B, and therefore this is a trade-off between time and space. A similar idea can also be used to store part of the suffix array in memory. Finally, let's see the whole algorithm in action using the query AT. Since we are going to look for the characters in the query backward, first we need to work on T. From the O table or by other means, we can easily find out that the indexed sequence contains 4 occurrences of T. Next, we want to find out where they are in the first column of the sorted rotation matrix. We do it by checking the F table. From the T entry of the F table, the first occurrence of T is at position 8, and therefore the 4 occurrences will occupy row 8 to row 8 plus 4 minus 1, that is row 11. Now we want to know whether the last column of the sorted rotation matrix contains an A in these 4 rows. From the O7A entry of the O table, we find that before entering row 8, we have seen 2 8s. Then from the O11A entry of the O table, we find that up to row 11, we have seen 4 8s. Therefore, we can infer that these 4 rows contain the third and fourth occurrences of A in the last column. Next, we want to find out the rows that these A's occupy in the first column. Since the first A appears in the second row according to the FA entry of the F table, these 2 occurrences of A must appear in row 2 plus 1 minus 1, that is row 4, and row 2 plus 4 minus 1, that is row 5. Finally, we go to the suffix array and extract the numbers at positions 4 and 5, which are 2 and 6 respectively, and conclude that S contains 2 copies of AT at positions 2 and 6. With that, the whole searching process is complete.